So, hello everyone. Thanks for the introduction. My name is William Godoy. Today I'm going to talk about JACC, Overall Performance Portable Programming Model in Julia. So, I want to thank my colleagues Pedro and Jeff. Oh, sorry, thank you. Pedro did a lot of core work. It was a collaboration between the two. I'm part of the Computer Science and Math Division at Oak Ridge National Lab. So this is the overview of my talk, where the motivation, why we're doing what we're doing, some of the description of the package, how Julia new features are helping to work on this. I'm going to show some results on our supercomputer summit and frontier, and finally the conclusions and final thoughts. So, oh, by the way, I'm part of the Julia for HPC community, so check it out. We have above later. This is part of our presentation we had yesterday too. So the motivation is that performance portability might be a niche problem if you compare to the broader, landscape of computing. We run on x86, and if you buy GPUs, usually NVIDIA, right? But places like the Department of Energy, we diversify the investments, building machines that are heterogeneous, usually GPU accelerated to different vendors. So it's a requirement, And here I put the graph of the top 500 supercomputers to, realize that, yeah, we're niche of the niche, like heterogeneity, but it's coming, right? As we hit the, limits of Moore's law, we're going to see more heterogeneous hardware architectures, vendors, and all that. So this also came out of feedback from our first ever BOF at supercomputing, like, oh, what is a portable layer? Portable as in, can I write code and run it on different architectures? So you have, oh, and by the way, this is just self-promotion. So we're always looking for collaborations, check jobs, internships, and you are interested. So we are national labs, essentially, always looking for this type of collaboration, funded by all of you. JACC. So we try to explore, something that didn't exist in Julia, right? You have things like kernel abstractions to write your kernels for performance portability. But what about, something that looks like COCOS, functional programming, We talked to Valentin about it. It's like, oh, we're exploring this idea. Because in the DOE, you have things like COCOS that is funded in the DOE ecosystem. So we use a functional approach. We don't want to reinvent the wheel. You guys are doing a wonderful job with the backends, right? You have CUDA, AMD, GPU, JL. So one day we'll have access to Intel GPUs, we'll start trying preferences. So we reuse rather than reinvent. This is the motivation. This is for the scientist that comes and says, you tell me Julia is easy. Can I just write the code and it will run everywhere? If you do it with CUDA JL, it won't run on Frontier, for example, right? So what we're reusing is the capability of weak dependencies. For example, your backend is going to be, redirected depending on, your functionality will be redirected depending on the backend you choose. So that's the structure. We only support Julia 1.9 and onwards, right? This is very futuristic. And we include scores and fine granularity parallelization, right? On CPU, typically scores, on the GPU accelerators, you have fine granularity in which you have to select, the tiling, the really, a small job kernel. I'm gonna go through those slides, what I mean by that. So we want to put the word out there, really simple for science, right? And just like with COCOS here on the right-hand side, we're trying to be descriptive, not prescriptive. What does it mean? Like, oh, just give me your function, give me what you need, and we'll take care of the backend. So here you have an example, right? What are the main components? It's essentially the memory allocation and the ability of, just passing a parallel forward. These are very common in the HPC applications, world. So common mathematical kernel, JACC, right? You just write that function. This is what you want. And then, you write this once, and then it should work on CUDA, it should work on AMD GPU, it should work on your CPU threads, that adds simplicity. So not only that, we take advantage of Julia, for example, we just alias, the array that Q array give us, that ROCm array give us. And then, we can put variadic arguments, right? You can put your function is your function. You can pass, anything that you can. We have to overload this. I'm going to show that later, So your function is an argument, just like funters, nothing new. So internals, as I mentioned, uses weak dependencies. So if you look at one of your backends, it's going to look like this for threads. The same is going to look like this for CUDA, the CUDA implementation. You just overload, essentially. And, we also explode multiple dispatch because, okay, this is just for one-dimensional arrays. What about 2 or 3, depending on the science, right? What the scientists need, right? In Fortran, you have to also optimize this for the number of dimensions that your array have. So these are our results. As I mentioned, this is very experimental. We expect a lot of feedback. This is more of part of our research agenda rather than development, right? We expect people to have a taste of what Julia can do by just, okay, I want to write this kernel here, and run it on different platforms. So we have results. Here are the characteristics of Summit and Frontier. They both have GPUs. Summit is powered by NVIDIA B100s. Frontier have the latest MI250X GPUs by AMD. And here, what we're trying to look at is like, okay, this is not adding much overhead. This is a very lightweight layer on top of the wonderful backends you guys have put, right? So if you run on CPU threads, here higher is better, right? So blue is CPU threads. Most of the computing power in these machines come from the GPU. You expect that acceleration, right? So this is why we're doing this. This is what the scientists will see with their kernels if they are parallelizable. So we grab typical examples, right? These are very common kernels, Saxby, conjugate gradients, lattice Boltzmanns, and we see that. You can see also NUMA effects and things like that, depending on the nature of the kernel. So conclusions, final thoughts, we are presenting this performance portable, functor-based programming model. Think of Cocos. What if Cocos was written in Julia? These are not new ideas, but there's no implementation today. So the motivation, we try to keep programming in Julia as simple as possible, especially for scientists who don't have time to program, but to write papers, and overhead is minimal. And we want to expand it to relevant things and the DOE, especially the kernels we want. Feedback is welcome. Here is the repo, and I want to acknowledge, my sponsors, ECP, the facilities, of course, the projects that fund me, the package maintainers, and as I mentioned yesterday, if I'm missing someone, please let me know. I'm very grateful for all the job you put, and we're organizing a workshop at Supercomputing, so everyone's welcome to do that. Thank you very much. All right on time.
Thank you. Are there any questions?
Compared to the code cost, how much? What's the code complexity of JACC?
Thank you, Johannes. I knew you were going to ask that. The question is, compared to Cocos, what is the code complexity compared to that? We are essentially banking on Julia, productivity. So Cocos is C++. Cocos is, you work for the C++ programming model with lambdas, templates, etc. We just bank on, you saw the two components. Array, it looks like a lot like, any of the arrays on the backend, and, parallel force. That in any ways, the better comparison will be with Fortran. It's much closer to Fortran because it's Julia. Yes, Simon.
I guess the question is like, how do you envision it to use versus say something like kernel abstraction, which is also
yes.
performance portability kernel, but also inspired by different SQL.
That's a great question. Thank you, Simon. The question is, how do you envision this being used or differently from kernel abstractions? Is that a fair? Yeah. No. So we talked to Valentin about this. It's essentially, we asked him like, this is yet another way of programming, right? Functional approach. Kernel abstraction essentially following the CUDA model, right? CUDA JL. It's like, hey, yeah, you don't have to write. It's like, what if you write things in CUDA that can work also on other GPUs? So it's specifically for GPUs. It's not really targeting CPUs. But as we show, CPUs are important in HPC still, right? So the way we want to tackle is like, look, it adds to the portfolio. It doesn't try to, if you're happy with kernel abstraction, of course, use it. It's well maintained. We're just scientists exploring this way of doing things and say, oh, if it works for you, go ahead. You have a.
Maybe the question is like more like where you see like a use case would be. I mean, I guess you said the GPU specific one, but if I'm a scientist, which one should I pick? Like where should I?
So the question is, as a scientist, which one should I pick? So if you're coming from Fortran, you're going to be very familiar with this parallel for. That's essential target audience. You're not necessarily familiar with GPU programming, but you're familiar with parallel force. Does it make sense?
I think the rest of the questions can be taken offline.
Yeah.
Let's thank the speaker once more.